Welcome to a video on BJT low frequency response analysis and design. Now, we can treat these together because when you did the analysis, the design is only one more step, or basically the same last step as the analysis would be. So, we are going to analyze the amplifier to a point, and then we will just design the capacitor values from there on. So, in this video, we will be looking at the analysis rules, and then we will be looking at some examples. So the common emitter with a bypassed emitter, common emitter with a emitter resistor present or extra, common base, and common collector. So just as a reminder, the low frequency model that we will be using for our transistor is just R pi and the current source. And then for a common emitter, the low frequency capacitors would be the coupling capacitors and the bypass capacitor. For the low frequency, if you calculate the frequency for each one of these capacitors and its seen resistance, you can just add all the frequencies together and that will give you the low frequency. So if you ever need to do an analysis completely, just calculate all the resistors, multiply the caps, and finding the frequency of each, you can just add them. If you're doing a design, then each one of the capacitors has a contribution of the frequencies, and for a common emitter it's typical to have 5%, 5%, and 90%. So if it's 100 hertz, this would be 10, 10, and 80 for the 10, 10, 80, and for the 5, 5, 90, it would be 5 hertz, 5 hertz, and 90 hertz. So there is typically ratios like these. For the common base, your coupling capacitors is again low frequency, and then the capacitor used at the base is also a low frequency capacitor. Now, typically, the one carrying the most weight when designing in the common base would be the input capacitor, and since you typically match the input and the load of a common base, this is a typical place to put it, and that is a very low resistance in any case. So that that capacitor right there is the important one in the end, and it just works better for capacitor values to design for CC1 here. And again, we have the same ratios. Then for the common collector, we just have the two coupling capacitors, and there it's typical just to divide it up 50% between the two caps. Okay, so for the analysis and design, remember that all high frequency capacitors becomes open circuits. Then you can use the Q point to calculate all the small signal parameters. Then you switch off all the DC voltage sources. They become short circuits to ground. If there's current sources in them, they are infinite impedances, so they become open circuits. Replace the transistor with a low frequency model. Keep all the low frequency capacitors in the model, don't remove them like you did with this small signal analysis of the amplifier. And then we are going to evaluate each capacitor separately and check the resistance seen by each capacitor in series, and then we can either calculate or design for the lower cutoff frequency. So if you have capacitor values available, you can just analyze, and if they're not available, you can design. So all the problems is going to be design problems, all 4 of them. But I'll show you where what you can do if a capacitor value is actually just given to you and you need to find the low frequency. So example 1, all the amplifiers that I'm using here we did in previous problems. We did the analysis for the small signal on these. So I'm just going to give the collector current. So this amplifier is biased with 140 microamperes and has a beta value of 200, typical for the 2N quad 2. So first we need to draw the low frequency model of the amplifier. Then we calculate the small signal parameters. Then we calculate the resistance seen by each capacitor. And then we are going to design for a lower cutoff frequency of 1 kilohertz, and CC1 and CC2 should contribute 10% each, and we should select standard capacitor values. Right. So you should be very good at drawing models at this point. And keeping all our capacitors in, this picture looks a bit different than normal, but it's not a problem. So calculate the small signal parameters because we are going to need R pi. And let's start with CC1. If we want to see the impedance seen by CC1, we are going to short these 2 capacitors. Not that shorting this one means anything to us, but let's short them. If this one is shorted, RE is removed from our circuit. Now we need to check what this capacitor CC1 is seeing in series with himself. So it sees RS and it sees in this direction RB in parallel with R pi. So RCC1 is RS plus RB parallel with R pi. So that is our first equation. Our second one is when this is shorted and this is shorted. Not that it matters because we are not going to see in this direction from the perspective of CC2. So CC2 sees in series with itself RC. We don't see past this because it's the infinite impedance as a current source. And looking in this direction, we see R load. So CC2 of RCC2 is R load plus RC. That's 43 kilo ohms. Right, and then the last one is when CC1 is a short and CC2 is a short. Again, we do not see in this direction, but we are seeing in this direction. Now what CE sees when looking in that direction is RE going to ground. And then on this side, continuing, it sees RS and RB in parallel with one another. Okay, so they are in parallel, plus R pi. But we are all seeing this through the transistor backwards, so it should be divided by beta plus 1. So we have RS parallel to RB plus R pi divided by beta plus 1, and all of that is in parallel with RE, like what we have down here. This capacitor will typically see a very small impedance right here, so it will mostly be the effect of these brackets over here, because the RE that we use for biasing purposes is typically very large. And looking back here, we see 211 ohms. And where is our free resistances calculated? Now, F load is FCC1 plus FCC2 plus FCE. Right, so if we had capacitor values, we could have just calculated FCC1 by using the resistor and the capacitor that's in the circuit like this. So 1 over 2 pi RC, the typical 1 over 2 pi RC equation. So then you can calculate that for all three of them and just add the results together, and that will be your lower frequency. Okay, for a design, however, we need to design for 1 kilohertz, and the specification said that FCC1 and FCC2 should be 10% contribution of 1 kilohertz, and 0.1 of 1 kilohertz is 100 hertz, 0.1 is 100, 0.8, 80% is 800 hertz. So 800 plus 100 plus 100 should be 1K. Right, now we just take the 100 hertz and the 29.8 kilo ohms that we got, and we plug it into this equation, and we can rewrite it as coupling capacitor 1 is 1 over 2 pi resistance seen by coupling capacitor 1 multiplied by 0.1 F low frequency. That gives us 53.4 nanofarads, and the closest standard value is 68 nanofarads. If you choose this a higher value, however, the frequency will move to a lower point. Right. The next one is RCC2. So we go through the same process and we get 37 nanofarads, and we choose the closest 3 nanofarads. So this is a lower value than this one, so our frequency will move up again. Right. Then for the common, for the emitter capacitor, I found this to be 943 nanofarads basically, and I chose it to be 680 nanofarads, which is downwards, which moved our frequency a bit up. And when I was simulating, I found that picking this 1 microfarad is too far of a jump with this low resistance here, and it moves our frequency too far away. So I went with a lower value right here. If you pick this 1 microfarad right off the bat while you're designing, that is okay. There's no problems with that. I chose a lower value because I did the simulation on this and saw the effect that this 1 microfarad capacitor had in this position. Right, so let's have a look at the simulation with these values in it and check out the frequency response. Right, so here is our simulation, and let's run it and check our output here. If you bring up our cursor, we see that this is about 20.6 dB, so we need to be looking for 17.6 in this direction. So 17.6 is around here, so that is 1.07 kilohertz. So our selected values, this is pretty close to what we wanted it to be. Let's make this 1 microfarad, and let me show you what I mean. is this frequency moved by a lot now, right? So 17.5 was it? That is now at 747 hertz. Okay, so the values that you calculate for the capacitors in the end will give you a rough idea of what you should be selecting. And because you are selecting standard values, you might encounter some major jumps. And this one we chose differently, this one we chose differently, and now this one. So the values that you calculate will give you a rough idea, and then you can play around with them to find suitable values. But I think in the end the design went quite well. Okay, let's look at the next example. Right, for example 2 here, we have this extra emitter resistor included, and now we want to design for 300 Hz, and C1 and C2 should contribute 5% each. And we are going to go through exactly the same steps as the previous problem. So if you want, you can pause this and see if you can set up the equations yourself and the model, and then unpause when you're ready and check if you got the same results as I did. Right, onto the model. The only difference between example 1 and 2 is that now this capacitor is not going to ground, it's going through RE2 to ground, and that is the only difference. So CC2 still sees R load and R collector. That's it. CC1 still sees RS, but in the previous problem we only saw R pi. Now looking into the transistor, we are going to see R pi and these two resistors in parallel when this capacitor is shorted. So we will be seeing RE1 parallel with RE2 viewed through the transistor, so multiplied by beta plus 1. Add that to R pi, and this will all be in parallel with RB. Okay, so we will have RS plus this whole thing right here. Now, another way to look at this, when we were just working with a plain amplifier, looking past this capacitor, this was Z in. This whole thing right here is Z in. Okay, so if you did calculate Z in at some point, you can just add it to the source resistor. Right, RCE. Now that is when this capacitor is a short. So first things we see RS and RB is in parallel, and this parallel combination is in series with R pi. They are viewed through the transistor, so they need to be divided by beta plus 1. And then this series combination is in parallel with RE1. So we have RE1 parallel to R pi plus the parallel combination of RS and RB divided by beta plus 1. And that is this one right here. And all we need to remember is that we are looking in both directions from this capacitor, so we need to add RE2. That yields a slightly larger impedance than the previous problem. 358 ohms. And now we need to design for 300 hertz with 0.05, 0.05, and 0.9 times our lower frequency. Okay, so 300 hertz, that will be a 15, and a 270 hertz. If we calculate them, we will come up with a 984 nanofarad capacitor for our input. So we're going for 1 microfarad. For our output coupling, we got 286.8 nanofarads, and the closest large capacitor value is 220 nanofarads. Not 270, it's 220. Right. And then lastly, so this one is picked lower, this one is picked lower, that one is picked higher. Lastly, our 90% contribution gives us 1.65 or 1.5 microfarads. Okay, let's check out our simulation and see if we reach our 300 Hertz specification. Right, here's our simulation. Let's run it. Check our output. Open a cursor, and our midband here is 19.9, so 20 dBs. We will be looking for 17 decibels. 17 decibels, 298.7 hertz. That is very close to what we designed for. Right, so we reach our specification. Designing these capacitors is actually quite easy. If you want this bandwidth this way to increase, you just make these capacitors as large as you want. You would have seen in the previous simulations that this would have been something like 100 microfarads, this 1 micro, and that is already 1 micro. If you run this, look how this bandwidth increases, and just with that, our lower frequency is at 17.36 hertz. So if you want almost all the frequencies to pass, just make these capacitors as large as possible. Just remember, if they are too large, they need to charge up in the beginning, and your circuit will be a bit on the slow to increase its gain on the output side. It will look kind of funky, and if you use electrolytics here, yeah, your output can start to look kind of strange. Just keeping that in mind. Okay, on to our next example. Our third example here is a common base amplifier. So this amplifier is biased at 200 microamps, and we need to design for a low frequency of 10 kilohertz, and the base capacitor and our output coupling capacitor should contribute 5% each in this one. But let's have a look at the analysis first. So RB is not bypassed or not disappeared like the small signal, and we keep RB right here. The emitter and the source resistor kind of looks like the emitter resistors in the common emitter amplifier. And look, output coupling still just RC and R load. Okay, let's have a look first at We're not going to have a look at CC2. That is easy, and that is 60 kilo ohms. Let's have a look at CB first, and that is when CC1 becomes a short circuit. So we have RE and RS in parallel. They are seen through the transistor, so they are multiplied with beta plus 1. And then we add R pi, and this whole configuration is in parallel with RB. So again, this is just the same as the input impedance of a common emitter amplifier looking from the base capacitor. Right, so we have RB parallel with R pi plus beta plus 1 RE parallel to RS, and that gives us 5 kilo ohms. Then from CC1's perspective, CB is grounded, so RB actually disappears from this whole thing. And CC1 looks in this direction and it sees RS, and it looks in this direction and it sees RE in parallel with R pi, but R pi is viewed through the transistor backwards, so R pi is divided by beta plus 1. And we know this should be small re, which should be roughly the same as our RS if this was designed correctly. And in this problem, it gives us 249 ohms. So always remember series with the capacitor. And this is RE parallel with small re, and that is the input impedance of this amplifier. Right, on to the design part. We're designing for 10 kilohertz, and CC1 is going to be carrying 90%. So if we calculate that, since it's a very small value, we get 71 nanofarads, and that is 89 nanofarads on the input. CC2 is with a 60 kilo ohms, and that gives us 5.3 nanofarads, or the closest is 4.7 nanos. And for 5 kilo ohms, we get 63 nanofarads, and the closest is 68 nanofarads for our base capacitance. Okay, so the moment that you got these equations down, either further analyzing or designing would be very easy. So just remember how to work with the model and how to get the impedances that you are seeing, and calculating capacitors for these problems will be a breeze. Okay, let's look at our simulation. Alright, simulation, let's run it. And our output. Switching on our cursor, our midband gain is 35 decibels, so we should be looking for 32 dBs. There we go. 32 dBs, and this is sitting at 9.09 kilohertz. That is very close to 10 kilohertz. You can then just tweak some of your values to get better results. So if I open my capacitor table here, we are looking at the nanofarad range. And we picked a 4.7 nanofarad where we had 5.3 nanofarads right here. So .1 is available. So if we run this now, not much has changed with that choice. our main culprit will be this one over here. So let's see, 68 is highest. If we want to go higher, we need to go with 100 nanofarads, and that is not going to be helpful to our problem at all. So you drove a frequency downwards. So if you look for 42, that is now at 6 kilohertz. Choosing it down would be 400 and so it should be 47 nanofarad. And now it's at 13 kilohertz. Okay, so if the contribution is the maximum, that is the most sensitive capacitor of them all. So take care with your selections. Just a warning. So this should be 68 nano, and that gives us the closest and best result. Right, on to the common collector problem. Right, here is our common collector, and it's biased at 150 milliamperes. And we need to design for 100 Hertz, and CC1 and CC2 should contribute 50% each, so 50 Hertz on each capacitor. So here we only have the 2. And let's have a look at our model with the capacitor. So let's start with CC1. So CC2 will be a short. And looking in here, we see these two in parallel now, multiplied by beta plus 1 plus R pi in parallel with RB. And we should add RS to this. Right, so we have RS plus RB parallel to R pi plus beta plus 1 RE parallel to R load gives us 1.45 kilo ohms. So again, the input impedance of a common collector amplifier plus the source resistance. Then on the output, if we short CC1 and we look backwards, we see R pi plus the parallel combination of RS and RB divided by beta plus 1 would be in parallel with this RE over here. And that final result plus our load would be our impedance seen by CC2. So R load plus RE parallel to this parallel comp plus R pi over beta plus 1 should give us 151.9 ohms. And that is it for the common collector analysis. Now designing for 100 Hertz, it's 50 Hertz each capacitor. So first capacitor is seeing 1.45 kilo ohms. We calculate that, we get 2.19 microfarad or 2.2 microfarads, and the 152 ohm resistance sees 20.95 microfarads, and that is basically a 22 microfarad capacitor. Quite simple. So let's have a look at our simulation. Right, let's run this. Check our output. Open ourselves a cursor, and this is minus 4.6 dBs. That is due to the input loading effect. That's why it's not 0. So we need to be looking for minus 4, 5, 6, 7, minus 7.6 decibels. Minus 7.6 dBs is at 77.64 hertz. We picked this one 2 microfarads larger almost. So this gives us a rough idea of what to expect. But yeah, that is the common collector. Really easy to design for a common collector in the end of the day. Our load carries the most contribution in any case, so we could have worked with just our load. And since the input impedance of this one was designed to be about 1 kilo ohm, 1.56 is very close to the 1.45 that we had, would have also worked out quite fine. But yeah, that is the common collector, and that is analyzing and designing low frequencies for our different BJT amplifiers. So I hope this was helpful, and good luck in the future with choosing your capacitors. Thank you for watching.